Okay, guys. So far, we have got familiar with the idea of sampling, and in continuation, we are going to discuss very important topics related to sampling. Okay. Proposition number 8. The following signals are sampled with the sampling time Ts. Determine the bounds of Ts in each case to guarantee no aliasing. Okay. We remember the definition of aliasing. S should be greater than or equal to 2 times maximum frequency in signal. Okay. Two cases. X1 of t is equal to cosine of 10 times pi times t multiplied by a sinc. This is a sinc in time domain. And we have multiplication in time domain. This is the first case. And the second example, x2 is related to convolution of two signals in time domain. Right? The first one is the response of a low pass filter. Later we'll get familiar why it is correct. Okay? Say it, the first signal, which is convolved with a sinc in time domain. The width of the sinc is W. All right. Solution for the first case. I mean this signal. Right. This is an amplitude modulation, AM. The cutoff frequency of the impulse response of the low pass filter is equal to P or pi. Pi is correct, but I myself prefer to pronounce it P because it's simple for me. Anyhow, we don't have any problem about the pronunciation. This is not English lectures, just teaching English. And I am not special in English talking. Anyhow, the spectrum is shifted by plus minus 10 pi. Why? Because it's a cosine. It has 2 Dirac in the relevant frequencies, plus minus 10. Okay? So, omega S1 should be greater than 2 times 10 plus 1 times P or pi. 10 is related to the first one, and the duration of pulse in a frequency domain. It is sinc in time domain, so it will be a pulse in frequency domain with such a width, 1 pi. Altogether, 10 plus 1, 11 pi times 2, twice the aforementioned bandwidth. Okay? It's related to radial frequency. So, sampling time needs to be less than 1/11 second. Very simple example. Okay. What about the second one? Solution for the second case. Multiplication in time domain just means that their spectra will be convolved, or convolution of their spectra. Right. I need to change the slide, hoping that you have written down this equation. Meanwhile, we remember from Laplace transform that if the signal in time domain is v1 of t equals to e to the power of minus 4 times t right-handed u of t, therefore its spectra will be 1 over S, say it V1 of S will be 1 over S plus 4. We substitute S for J omega. Therefore, V1 of J omega or V1 of omega will be equal to 1 over J omega plus 4. If we imagine the amplitude, which will be 1 over square root of omega to the power of 2 plus 16, in frequency near 0, we'll have 1 over 4. The amplitude will be 1 over 4. And when omega approaches to infinity, the amplitude will go through to 0. So it behaves like a low-pass filter, right? Just oral conversation. But going back to lecture note, which means that the spectra is spread from minus infinity to infinity. However, the spectra of the second signal has a shape of pulse because it was a sync in time domain. So it will be a pulse in frequency domain with width equals to capital W. Therefore, the multiplication of two spectra will have a width of W because it will truncate the rest of the spectra beyond the width of W. Right. Therefore, it leads to having capital omega S2 needs to be greater than 2 times W, or meaning that sampling time needs to be less than P over W second. Very simple